All right, welcome to lecture 5.6 covering rational functions. Okay, so I wanted to start off this lecture with an example that was posed in the book to help you understand why we even need to look at rational functions in general. The first thing is I'm going to show you a typo here. Let me actually get a white pen so that I can correct it. This came out incorrectly on the notes. That should be an x squared term right there. So I'm whiting that out and then making that an x squared term. Okay, so suppose we know that the cost of making a product is dependent on the number of items x produced. This is given by the equation C of x, in other words, the cost, is equal to 15,000x minus 0.1x squared plus 1,000. If we want to know the average cost of producing x items, so in other words, this big polynomial equation here is giving you the cost, the total production cost of, however many items you ended up producing. However, if you want to know how much it cost you to produce one of those items, you would need to divide that polynomial by x, which x is standing for an item. So you now have the average cost function given below there of that polynomial being divided by x. This is an example of a rational function. The reason this is considered a rational function is because we have a variable in the denominator. So don't forget, and this is what this little paragraph below says, if we remember our rules of exponents, if we brought this up to the numerator, that would become a factor of x to the negative first power. Because right now it's an x to the positive first power in the denominator, so if we bring it up, that power becomes negative. So this is the difference between a polynomial function and a rational function, in that our definition of a polynomial function said we had to have positive exponents only on our variables. So rational functions incorporate negative exponents, but we don't show them as negative exponents, we just put them in the denominator. So a rational function is one that is going to have a variable in the denominator. All right, so let's talk a little bit about arrow notation. Okay, so to fully understand rational functions, we have to look a little bit more about the end behavior of the two toolkit or parent rational functions that we discuss in this particular section. And we use arrow notation, and we've already discussed this in a previous section, but we're going to look at it a little more in depth here. We use arrow notation to describe how the tail ends of these functions are behaving. So let me just write what functions we're looking at here so that you can see them. I'm going to write them a little bit bigger. This first one is the rational function 1 over x. And the second one is 1 over x squared. Okay, so what we're talking about with end behavior, obviously, is the tail ends. And since these particular functions have breaks in them, we have a lot more than just two tail ends to worry about. We've got 4 in both of these in their parent function, and we can have more. It just depends on where you have asymptotes and stuff like that, which we'll discuss here in a moment. Okay, so I'm just highlighting the tail ends here. Let's look specifically at 1 over x. So we're going to start with this one here. And if we look at this first tail end, the leftmost, it looks as if that graph is getting closer and closer to the x-axis. However, this graph is never going to cross the x-axis. And that's because the more negative you go in your input values, the closer you get to 0, but you actually don't ever get to 0. So if we have f of x is equal to 1 over x, let's say I plug in an x value of negative 100. That's going to come out as negative 1/100th. So that's an extremely small number. It's almost 0, but it's not 0. So you can see the further you go in the negative direction, think about plugging in negative 1 million. That would be negative 1 over 1 million, but it's not 0. So this is what we call an asymptote. And an asymptote is a line that well, it's an imagined line, so to speak, a boundary that your graph approaches but never gets to. So we have a horizontal asymptote and we have a vertical asymptote with both of these functions. So here's the horizontal asymptote for 1 over x squared, and here's the vertical. And these shift around depending on how you translate your function. So if you shift it to the right or the left or up or down, those asymptotes can move around with it. Okay, so back to end behavior. Let me just make a little more room now that we understand what the asymptotes are. Okay. So as my x values are approaching negative infinity on my 1 over x graph, my rational function graph, as those x values go more and more negative, my y values, or my output, get closer and closer to 0. We write that as x approaches negative infinity, f of x, or my y values, approach 0. I'm moving closer and closer to 0 there. Now let's look at this tail end. So we can see we go down into negative infinity in our y values, but in our x values, we're actually approaching an x value of 0 there. So for that tail end, as x approaches, we just use the arrow to show approaches. As x approaches 0, we have to tell which way we're approaching a value in our x's from. I'm approaching 0 from the negative x values. So I have to note that as x approaches 0 from the negative values, my f of x, or my y values, are approaching negative infinity. It's going down, 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 down. Okay, let's look at the other two tail ends. Let me get a different color for those. So here's why we have to tell which way we're approaching a value from in our x's. As x approaches, you can see x is getting closer and closer to 0 here too, but it's coming from the positive side. f of x approaches positive infinity. And then this last tail in, pardon me, this last tail in here, as x approaches, well, it's approaching positive infinity there, we're getting more and more positive in our x values. F of x approaches, it looks like it's approaching the x-axis, so 0. Okay, let's take a look at 1 over x squared. So to the negative side of the origin, we have as x approaches, okay, so this first tail end, this leftmost, my x values are moving more and more negative. So as x approaches negative infinity, f of x is approaching 0 as well there in its y values. Here's where it's different from 1 over x. As x approaches 0 from the negative side, f of x is approaching positive infinity. So we can see we're shooting straight up here, approaching positive infinity in our y value. All right, to the right of the origin, we've got this tail end right here. So as x approaches 0 from the positive side, f of x approaches positive infinity. And as x approaches positive infinity, f of x approaches 0. That is how you note tail end behavior using arrow notation. Okay, I had a blank page there. Let me just make sure I haven't skipped over any notes in our note sheets. Give me 2 seconds just to check this out. I might have just accidentally put in an extra page. And I believe I did. Yep, we're good to go. Pardon me. I don't know why my throat is dry this morning. Okay, so local behavior of f of x equals 1 over x, and end behavior of f of x equals 1 over x. Okay, so we can see that the behavior of this graph here to the left, and that's 1 over x there, it creates what we call a vertical asymptote. Okay, so what this is saying is, here's my vertical asymptote right here. It's going to get closer and closer and closer to that x equals 0 vertical line, but it's never actually going to get there. So here we go. As the graph approaches it, but never crosses it. In this case, it's approaching x equals 0. And this is the non-transformed version, or the toolkit version of this function here. And then we also have the horizontal asymptote, which not all rational functions have a horizontal asymptote. All rational functions will have a vertical asymptote, but not necessarily a horizontal. So based on the overall behavior of this graph, we can see that the function approaches 0, but never actually reaches 0. It seems to level off as the inputs become large or very, very small. So becoming very, very large in our inputs or becoming very, very small in our inputs. We approach that horizontal line, y equals 0. This creates a horizontal asymptote. Okay, so a general thing to note about each of these types of asymptotes. The vertical asymptote of a graph is the vertical line x equals a, where the graph tends towards the positive or negative infinity as the input approaches A. And we write, as x approaches A, f of x approaches positive infinity, or as x approaches A, f of x approaches negative infinity. A horizontal asymptote is a horizontal line, y equals b, where the graph approaches the line as the inputs increase or decrease without bound. In other words, as x approaches positive infinity or x approaches negative infinity, the outputs are approaching some given value. In this case, it is a value of 0. Okay, so some examples to look at of rational functions. I will go ahead and note that this first example on the left that we are looking at is the function f of x equals, okay, so it's got that same shape as 1 over x. However, we have been shifted from having the x-axis and the y-axis as our asymptotes to having a vertical asymptote at x equals 2 and a horizontal asymptote at y equals 4. Okay, so we have shifted 2 to the right and 4 up. Well, we can go back to our knowledge of transformations that we learned way back in the first test worth of material. And I know that when I shift right or left, or when I shift horizontally, that I am adding or subtracting from the variable in the function. When I shift vertically, I am adding or subtracting on the outside of the function. So the equation for this particular example would be, let's see, I have my basic form of 1 over x, except I've shifted to the right 2, so that makes this x minus 2, and then I've shifted up 4, so whenever I shift left or right, it's on the variable itself, and when I shift vertically up or down, that happens on the outside, so I'm going to add 4. Okay, looking to the right, oh, I'm sorry, it said to use arrow notation. That's what we were talking about. I got caught up in the graph itself. But use arrow notation to talk about the end behavior of this graph. Okay, so we will color code these. We'll first talk about the end behavior on that part of the graph. So we can see as x approaches negative infinity, so as I move more and more negative in my x values, my y values or my f of x values are approaching positive 4. Okay? And as x approaches, okay, so we're moving this way now, and it looks like I'm approaching 2 from the negative side. So as x approaches 2 from the negative side, f of x is going down into negative infinity. Okay, other side. So here and here. As x approaches, okay, now we're approaching 2 from the positive side. F of x moves off into positive infinity. And then as x is moving into positive infinity, so as x approaches positive infinity, f of x approaches positive 4. Okay, so that is our end behavior for that particular graph. And then actually, we've already discussed this one on the right-hand side. This is just good old f of x equals 1 over x squared. I haven't shifted away from the origin or from the x-axis and the y-axis being my horizontal and vertical asymptote. So I'll just mark those. Here's my horizontal asymptote. That's at y equals 0. And here's my vertical asymptote at x equals 0. So let's look at these two tail ends. As x approaches negative infinity, f of x is approaching 0. As x approaches 0 from the negative side, f of x approaches positive infinity. Okay, other side. As x approaches 0 from the positive side, f of x approaches positive infinity. As x approaches positive infinity, f of x approaches 0. Okay, so we're asked to give a quick sketch of this graph here. Here's what we know. It is a reciprocal square function, so I know that the parent form of that is 1 over x squared. However, we have been shifted right 3 units and down 4 units. Okay, so I have my toolkit function that I start out with. F of x equals 1 over x squared. And remember, minus is in the form here. So I needed to shift 3 units to the right. Remember, if it had been left, that would have been x minus negative 3, so that would have been x plus 3 squared. And then I shifted down 4. Okay? And they ask us to sketch this graph. So since I went to the right 3, my vertical asymptote shifts from the y-axis right 3. And since I shifted down 4, my horizontal asymptote shifts from the x-axis to negative 4. Down 4. Okay. So, a sketch of this graph, we know what x squared looks like. We have done no reflection, so it's going to get closer and closer and closer to y equals negative 4, and then it's going to come and run along x equals 3, but never actually get there. And then looks like a chimney to me. I always think about a chimney when I graph this function. All right, there's a sketch. Okay, so a general note about rational functions themselves. I did skip problems, I think. I just realized where do those problems come in? I'm talking to myself now. Okay, we haven't gotten there yet. All right, so a general note about rational functions. A rational function is a function that can be written as a quotient of 2 polynomial functions. So that's all that definition is down there. It's polynomial divided by polynomial. That's what a rational function is. Notice you have to have a variable in the denominator. Okay, so we are asked to write rational functions that model these situations. Okay, so a large mixing tank currently, let me highlight some important words here, currently contains 100 gallons of water and 5 pounds of sugar. If a tap that is opened pours 10 gallons per minute of water into the tank, while at the same time pouring 1 pound of sugar into the tank per minute. It says to find the concentration, pounds per gallon, of sugar in the tank after 12 minutes. And then is there a greater concentration than at the beginning, what we started out with? So here's what we know. We know that we start, before we ever open the tank, before we ever open the tap, there's already 100 gallons of water and 5 pounds of sugar in there. My water comes in at 10 gallons per minute when I open the tap. And my sugar comes in at 1 pound per minute when I open the tap. Those are linear relationships. Those have a constant relationship of coming in at 10 gallons per minute and 1 pound per minute. So that's why they're linear, because that change is constant. All right, so to figure out the concentration of sugar to water, I would divide. So my concentration function based on time has got to be C of T. Okay, so C of T is standing for concentration of sugar to water. To water. And that has to be equal to, oh, by the way, T is standing for time in minutes. So my concentration has to be equal to the amount of sugar based on the time that that tap's been open divided by the amount of water based on the time that the tap was open. So that's what I'm going to try to write. So what I need to do is figure out, how do I write my concentration of sugar as a linear function? How do I write my concentration of water as a linear function? And then I just have to divide those two to come up with the function that shows the concentration. So my sugar as a function of time, well, I know I started out with 5 pounds of sugar. And then I add 1 pound of sugar for every minute that that tap is open. There's my linear function for concentration of sugar. And then I have water as well, based on amount of time the tap was open. I started with 100 gallons, and I add 10 gallons for every minute that the tap is open. So my concentration of sugar to water is equal to, well, 1T is just T. So 5 plus T divided by 100 plus 10T. There is your function that they asked for. But then they said, well, after 12 minutes, what's the concentration? So all you have to do to figure that out is do C of 12. So 5 plus 12 over 100 plus 10 times 12. That gives us 17 over 100 plus 120, which is 17 over 220. What this says is, after 12 minutes, I'll have 17 pounds of sugar diluted or mixed into 220 gallons of water. We usually give concentration as a decimal, and when I do that division of 17 divided by 220, that is a concentration of approximately, so I've rounded, 0.077. So a little less than 8% concentration. The last question that they ask you to think about, though, is that a greater concentration than what you started out with? Well, what I started out with, I started with 5 pounds of sugar, 100 gallons of water. When I do that division, I get 0.05. So you can see that I ended up with a greater concentration than what I started. That says concentration. I know it looks like scribble, scribble, scribble. Sorry. All right, moving forward. All right, here's another situation. We have 1,200 freshmen and 1,500 sophomores at that should say pep rally at noon. After 12 o'clock p.m., 20 freshmen arrive every 5 minutes. 15 sophomores leave every 5 minutes. Find the ratio of freshmen to sophomores at 1 o'clock p.m., so 1 hour later. And just to note, 1 hour is equal to, since they're coming and going in 5-minute increments, that's 12 5-minute increments. So 1 hour has 12 5-minute increments in it, because 5 times 12 is 60, and 60 is 1 hour. 60 minutes is 1 hour. Okay, so we want to figure out the ratio, the pep rally ratio, 1 hour later. So my ending function will be P of X. In this case, X is standing for 5, or the number of, let me rewrite this. X is going to stand for the number of 5-minute increments. So the number of 5-minute increments. And to find the ratio at 1 o'clock at the pep rally, I'm going to need to divide my freshmen based on 5-minute increments by my sophomores based on 5-minute increments. That's freshmen to sophomores. Okay, so the linear function for my freshmen says I started with 1,200, and every 5 minutes I added 20 freshmen. My sophomores, I started with 1,500, but 15 of them left, so I subtracted 15 every 5 minutes. So my function that I'm going to use is 1,200 plus 20 times X over 1,500 minus 15 times X. Okay, so don't forget, X is standing for the number of 5-minute increments. So the question is, find the ratio of freshmen to sophomores at 1 p.m. This is why I told you at the very beginning, 1 hour, or 1 p.m. is 1 hour later, and 1 hour is 12 5-minute increments. So I need to find P of 12. So that's 1,200 plus 20 times 12 divided by 1,500 minus 15 times 12, which is 1,200 plus 240 over 1,500 minus 180. And when I add those numbers together and subtract, or combine those numbers rather, I get 1,440 divided by 1,320, and I can start reducing this fraction. I know that they each have 20, a factor of 20 in them, so that's where I'm going to start. All right, so let me get a different color here. Okay, so if I divide 20 out of 1,440, I get 72. And if I divide 20 out of 1,320, I get 66. So right now, I have 72 over 66. They're both even, and actually I know that they both have a factor of 6 in them. So when I divide 72 by 6, I get 12. And when I divide 66 by 6, I get 11. So what this says is 12 over 11. All right. So when at 1 o'clock, I have a ratio of 1,440 freshmen to 1,320 sophomores, which reduces to a ratio of, for every 12 freshmen that I have at the pep rally at 1 o'clock, I have 11 sophomores. Okay, so moving forward with more on the graphs of rational functions here. The domain, so that's the input values, or possible input values. The domain of a rational function includes all real numbers except those that cause the denominator to equal 0. We know we can't divide by 0, and when 0 is in the denominator, that's what we're doing, is dividing by 0. So we have to discount any values, any x values that cause the denominator to equal 0. So we have examples here. To find out when the denominator is going to equal 0, you just set it equal to 0 and see what x values create that. So here, in this first example on the left, I have x squared minus 9 in the denominator. So I need to know, when is x squared minus 9 going to equal 0? Because when that happens, I'm going to create an undefined situation in the function. So I add 9 to both sides, and that gives me x squared equals 9. I'm using my square root property now, so I'm going to take the square root of both sides. Don't forget, you have to take into account the positive and the negative. So here, x equals positive and negative 3. Now, I also want to look at this in a factored form. So let's say we have f of x equals x plus 3 over, if I factored x squared minus 9, that's x plus 3 times x minus 3, and I used difference of squares to do that factoring. So for those of you that are having trouble still with factoring, to figure out how that one factors, you need to look up difference of squares. Okay, so down underneath this problem here is a graph. I want you to take note. I have a vertical asymptote at x equals 3. In other words, if I use the zero product property here, in my denominator, at x equals 3, I have a vertical asymptote. You might expect another vertical asymptote at x equals -3 because that makes the function undefined. But notice you don't have a vertical asymptote. What you have is a hole in your graph. This is where the graph is discontinuous. So here's the difference in your restricted values from your domain creating vertical asymptotes or creating holes in your graph. I know I'm going to have a hole and not an asymptote when that factor that created the hole, x plus 3 equals 0, so x is -3, when the factor that created the hole could have been divided out with the numerator. So when you can divide a factor out of the denominator with the numerator, that 0 at that point is just a hole in the graph. If the factor remains after you've simplified the function through division, then that creates an asymptote. So that's the difference in creating asymptotes and holes in your functions. Okay, let's take a look at this next one. It's already in factored form for us. So we need to know, okay, when is this denominator f times x minus 1 times x minus 5 going to equal 0? Well, I'm already ready to use the zero product property here. 5 does not equal 0, so I don't have to worry about that factor. X minus 1 equals 0 or x minus 5 equals 0. Notice neither of those factors divide out with a factor in the numerator, so these are actually going to be asymptotes. X equals 1, x equals 5, and here's a picture of it down below. Notice I have a vertical asymptote living at x equals 1 and a vertical asymptote at x equals 5. So it always happens wherever your denominator could potentially be made 0. Okay, so this is just a note on identifying vertical asymptotes. You want to factor the numerator and the denominator. Note any restrictions in the domain by setting that denominator equal to 0. Then you need to decide, okay, is this an asymptote or is it a hole? So you reduce the expression. I don't like the word canceling, especially when they spell it wrong. I think that's spelled incorrectly. This is dividing. Dividing common factors out of the numerator and denominator. Remember, if you can divide those factors out, that's a whole. It's not an asymptote. So these are where your holes live. And you have vertical asymptotes with the ones that do not come out of the simplified version. Okay, so this textbook calls those holes removable discontinuities. I like just saying holes. It's easier. Okay, so find the vertical asymptotes of the particular function here. Okay, so I need to figure out when will the denominator 2 minus x squared be equal to 0. And I do not like it in this form. I want to get it in standard form. Negative x squared minus x plus 2. I don't like my leading term to be negative, so I'm going to factor it out. X squared plus x minus 2. Off to the side, I'm going to show you the AC method just to refresh you on how to factor that polynomial. Y'all are lucky because I haven't been showing factoring lately, but I will here, even though I can do it in my head. So I need to find AC. the product. A is 1, C is negative 2. Pardon me. So that's negative 2. Now I'm looking for the factors of negative 2 that add to make positive 1, which is B, and that is positive 2, negative 1. I rewrite my function, x squared plus 2x minus 1x minus 2. Split it down the center. GCF, that's x plus 2 left over. GCF, x plus 2. Big GCF is x plus 2, and I have a leftover of x minus 1. So this is what this looks like. Negative x plus 2 times x minus 1. So I have x plus 2 equals 0, x minus 1 equals 0. Here x is negative 2. Here x is 1. Notice I can't divide either. So if I look at my function again and write the denominator factored, the numerator is 2x squared plus 5. I cannot make that any simpler by factoring. And then I have a negative x plus 2, x minus 1. There are no factors that divide out between the numerator and, and the denominator, so both of these are asymptotes. Vertical asymptotes, to be precise, not wholes. Okay, so we're taking a closer look at removable discontinuities. Notice in my denominator, 0 equals x plus 1, x minus 3. Okay, so I just got kicked out. 1 equals and 0. Got brought back x in. Is negative 1. I have not lost my whole recording. But I'm going to have to restart on this problem because it erased everything. Okay, so we already have the denominator factored, and we're just trying to see where we might have asymptotes or wholes. So x plus 1 equals 0, x minus 3 equals 0. Here x is negative 1, here x is 3. Now I need to decide, okay, is this a whole or is it an asymptote? And if you look back up at the original problem here, I can divide out that factor of x plus 1. That makes this a whole. I cannot divide out that factor of x minus 3, so this is an asymptote. All right, so if you look, this is a picture of the graph. Here's my vertical asymptote at x equals 3, and here's my whole at x equals negative 1. Okay, same thing here, removable discontinuities or vertical asymptotes. I'm just going to rewrite my function here. I have k of x equals x minus 2 over x squared minus 4. So k of x equals x minus 2 over, that denominator factors as x plus 2, x minus 2. Notice I can divide that factor of x minus 2 out. Okay, so 0 equals x plus 2 times x minus 2, so x plus 2 equals 0, x minus 2 equals 0, here x equals negative 2, here x equals positive 2. But because I could divide that factor of x minus 2 out, this is just a whole, whereas this is a vertical asymptote. Okay, next one. Next one's a little more challenging because we have factoring that has to be done. Okay, so f of x equal to x squared minus 25, and I do not have the room to show all of this factoring. So I'm going to do it in my head. My numerator factors as x plus 5 times x minus 5. It is a difference of squares. I have a GCF in my denominator of x, and I'm left over with x squared minus 6x plus 5. I can further factor that trinomial, so I still have x plus 5 times x minus 5 in my numerator, and then I have a factor of x, and then I have an x minus 5, x minus 1, and I use the AC method to factor that. All right, so I'm either going to have wholes or asymptotes when that denominator equals 0. So I have x equals 0, x minus 5 equals 0, and x minus 1 equals 0. Here x is 5, here x is 1. All right, so because I can oops, wrong one. Because I can divide out x minus 5, that's going to be a whole. And then I'm going to have a vertical asymptote at x equals 0 and a vertical asymptote at x equals 1. And I'll go ahead and show you all the graph of this one because I think it'd be a good thing to see. Let me just make sure that I have my Desmos calculator pulled up. Give me just a moment. Okay, there it is. All right, and I need to write down that equation so that I know what I need to graph. X squared minus 25 over x cubed. Actually, I'm just going to go ahead and type it in here because I don't have a pen next to me. X squared minus 25 divided by x cubed minus 6x squared plus 5x. X cubed minus 6x squared plus 5x. Okay, now I'm going to share my screen and show you this graph. Okay, so we had, and these graphs, the Desmos calculator doesn't show the wholes. So you can see I have the graph here. I'm just going to put that off to the side so we can focus on the actual graph. Okay, so remember we had a vertical asymptote at x equals 0. Let me just zoom out a little bit and see if we get a different picture. Okay, all right. Nope. Oh yeah, I didn't see that bottom part there. So here is our vertical asymptote at x equals 0. We also, let me play with the x-axis here a little bit. Let's go from, oops. Just took my graph off. Crap. Let me put it back on there. Let's see, it was x squared minus 25. Or I'll write it in its factored form. X plus 5 times x minus 5. That was in our numerator. And then I divided that by, I had a factor of x. I had a factor of x minus 5, I believe, and x minus 1. Okay, so now you can see where the holes and the removable discontinuities and the asymptotes live. Okay, so let me see if I can zoom in a little bit here. All right. Okay, so I have an asymptote at x equals 0, looking at my denominator. This factor right here, that's x equals 0. So you can see with this part of the graph that it's getting closer and closer to the y-axis, which is x equals 0, but it never actually gets there. It never will cross over it. I also have a vertical asymptote at x minus 1, so x equals 1. And you can see that's also this bottom part here. I'm getting closer and closer to 1, but I never actually get there. Now let's look at the hole. I should have a hole at x equals 5, but notice it's continuous on this graph because Desmos cannot show holes. However, if I click on it, you can see at an x value, if I can get back on it. There we go. It's not going to hold it for me. There we go. At an x value of 5, now it'll show the hole. I am undefined. Okay? Hopefully that was helpful for you to look at that graph because it took a lot of effort. So I hope it helped. Okay, so we're back here. Okay, so I am back, and now we saw when we first looked at the toolkit functions, rational function and rational square, we noticed there were also horizontal asymptotes. So we need to figure out how to identify the horizontal asymptotes. So that's what this next portion of the lecture is going to address. And then once we get done talking about all this and intercepts, then we'll put it all together and graph a couple of them. All right, so with horizontal asymptotes, if you have the degree of the denominator, which in this example is 2, being greater than the degree of the numerator, which in this example is understood to be 1. So when the degree of the denominator is greater than the degree of the numerator, your horizontal asymptote will always live as the x-axis, or y equals 0. So you can see I have a horizontal asymptote where a few of my tail ends are approaching the x-axis. Now notice, here's one huge difference between horizontal asymptotes and vertical asymptotes. Parts of your graph can cross over a horizontal asymptote. Only a portion of your graph has to be approaching it but not crossing it. But notice this part right here crosses right over that horizontal asymptote, whereas the asymptote is approached on the tail ends of this function. So horizontal asymptotes are a little trickier than vertical asymptotes are. Okay, another situation that we could have. Okay, we could have the situation where the degree of the numerator is greater than the degree of the denominator. So the exact opposite. And in this case, we get what we call a slant asymptote. Okay, this one is the trickiest one of all to find. So I'm going to show you how we got this slant asymptote at 3x plus 1, okay? So here's how we did it. If I actually divided 3x squared minus 2x plus 1 by x minus 1, if I did it using synthetic division, it would look like this. So I combine down, multiply, write my result, combine down, multiply, write my result, and I have a remainder here. If I have a remainder, this means I have a slant asymptote. And the slant asymptote lives at 3x plus 1. So that is the line, 3x plus 1. And that acts as an asymptote. Notice I also have a vertical asymptote at positive 1 because I had a factor of x minus 1 in the denominator, and that is where 0 would be created. So that's a vertical asymptote, and then I have a slant asymptote because I have a remainder when I actually do the division there. And the last case we have to look at with horizontal or slant asymptote, when the degree of the numerator is equal to the degree of the denominator. We have an asymptote at the line y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So in this case, the leading coefficient of the numerator is 3. The leading coefficient of the denominator is 1. So since the degrees of my numerator and denominator are the same, I have a horizontal asymptote at y equals 3 over 1, which is just y equals 3. So here's my horizontal asymptote going right through here. And then down at the bottom, just to reiterate this point, notice while the graph of a rational function will never cross a vertical asymptote, it may or may not cross a horizontal or a slant asymptote. Okay, so finding horizontal or slant asymptotes. Let's take this first case here. The first case, g of x equal to 6x cubed minus 10x over 2x cubed plus 5x squared. And notice the degree of my numerator is equal to the degree of my denominator. So n equals m. That's the degree of my numerator, n, divided by the degree of my denominator, m. So since those are equal, I'm going to have a horizontal asymptote at y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So I'm going to have a horizontal asymptote at 3. Let's look at the next case. The next case is when h of x equals x squared minus 4x plus 1 over x plus 2. Notice the degree of my numerator is greater than the degree of my denominator. So n is greater than m here. This is where we have to do the division and find out the slant asymptote. So I am going to do synthetic division here. Notice it's a -2 that I'm dividing by because that's x minus -2 in the denominator. And my coefficients are 1, -4, and 1. I bring down, multiply, write my result. Combine down, multiply, write my result. Combine down. I have a remainder. So my slant asymptote lives at x minus 6. It's that line. This is a slant asymptote. Okay, and case C, k of x equals x squared plus 4x over x cubed minus 8. The degree of my numerator is less than the degree of my denominator. That means I have a horizontal asymptote at the x-axis, which is okay. So a general note about intercepts of rational functions. A rational function is going to have a y-intercept exactly where every other function we've talked about has y-intercepts, and that is when you plug in 0 for x. If the function is defined at 0, because remember, it could potentially have a vertical asymptote there. So if it's defined at 0, you can plug 0 and that's where you're going to have a y-intercept. A rational function will not have a y-intercept if the function is not defined at 0. It's going to have an asymptote. Likewise, a rational function will have x-intercepts at inputs that cause the output to be 0. In other words, you're going to have a y-intercept when x is 0 and an x-intercepts at y is 0 or f of x is 0. And don't forget, this is as long as it's defined at those values. And so they make the other statement about x-intercepts that they can only occur when the numerator of the rational function is equal to 0. So that's how we find x-intercepts. We set the numerator equal to 0. Because remember, if the denominator is equal to 0, that's undefined. So let's go ahead and find the intercepts here. We'll do the easiest one first, and that's the y-intercept. So for the y-intercept, this is when x is 0. So we do f of 0 here. So 0 minus 2 times 0 plus 3 over 0 minus 1. Sorry, my writing's really bad. I had to move to a bedroom. I'm with my family on vacation, and they were getting really loud, and I couldn't even hear myself think. So I'm back in my bedroom, and I've got my tablet sitting on my lap. So I've never used a tablet in my lap like this. So that's why I'm off on my writing. -1 times 2. Oops, these are zeros right here. I'm sorry. 0 times -5. All right. And that gives me -6 over positive 10. So I have a y-intercept at -3/5. Now all I did was just divide it out, a 2 from the numerator and the denominator to simplify that that fraction. If you're looking for the decimal, that is -0.6. Okay. And my x-intercept, that is when f of x equals 0 or y, but I don't need to worry about the denominator because we know that that's where we find our vertical asymptotes or our holes. So I just need to set the numerator equal to 0. So 0 equals x minus 2 times x plus 3 And that happens when x minus 2 equals 0 or x plus 3 equals 0. There's our zero product property. So 2 and negative 3. Those are our x-intercepts for that function. It'd probably be a good idea to take a look at that on the graph. So let's see, x minus 2 times x plus 3. Well, for the sake of time, we'll go ahead and move forward. Okay, so if we are given the reciprocal square function that has been shifted right 3 and down 4, first write the rational function, and then find the x-intercepts, y-intercepts, horizontal and vertical asymptotes. All right, here we go. So reciprocal square that's been shifted right 3, here's the right 3, and down 4. There's our function right there. All right, but to be able to figure out x-intercepts, we need to have the numerator and the denominator, for that matter, to figure out asymptotes in factored form. But because we're subtracting that 4 out to the side, this is not in factored form. So I have to do a little bit of fractional math here. That's really a 4 over 1. I need to get a common denominator. So I have to multiply by x minus 3 squared over x minus 3 squared so that my denominators are common. And that gives us 1 over x minus 3 squared minus 4 times x minus 3 squared over 1 times x minus 3 squared is just x minus 3 squared. Okay, I cannot distribute that negative 4 into the parentheses because those parentheses are squared. So I've got to multiply that out first. This is equal to 1 over x minus 3 squared minus 4 times x minus 3 times x minus 3 over x minus 3 squared. All right, so this distribution goes here and here, here and here. And now I have 1 over x minus 3 squared. And actually, I'm the, well, no, never mind. Minus 4 times. Okay, so this multiplies out to be x squared minus 6x plus 9. And that's over x minus 3 squared. Now I can combine my numerators over my common denominator. But notice I have this distribution that also needs to be done, and that is a negative 4 that gets distributed there. So I'm going to do this in one step here. I have 1 from my first numerator, and now I'm going to distribute negative 4x squared plus 24x minus 36 over my common denominator of x minus 3 squared. Okay, and when I combine my 1 and my negative 36, I end up with negative 4x squared plus 24x minus 35 over x minus 3 squared. Now I have to factor the numerator so that I can begin to identify these different pieces. So that's what I'm going to do. My numerator, I'm going to have to give myself another page for this one. My numerator is negative 4x squared plus 24x minus 35. I don't like my leading term being negative, so I'm going to factor that out. And that's x squared minus 24x plus 35. I'm sorry, negative. This is 4x squared. Okay, so AC method, 4 times 35 is equal to, what is 4 times 35? I guess I should grab my calculator because I can't do that in my head this morning. 140. So I'm looking for the factors of 140 that add to make negative 24, and that's negative 14 and negative 10. So I rewrite. So I still have that negative 1 hanging out there. 4x squared minus 14x minus 10x plus 35. Just giving myself room to GCF these, factor by grouping. GCF here is 2x, and I'm left with 2x minus 7. GCF on the other side is negative 5, because I don't want that negative leading term. This is 2x minus 7 as well. So this thing factors as 2x minus 7 times 2x minus 5. Okay, so I'm just going to write this polynomial function in this form as well. So these are the same things. This is the same thing as negative 2x minus 7 times 2x minus 5 over x minus 3 squared. Okay, so I needed to do that not only to more easily find my x-intercept, but I also needed to see if any of my factors in my denominator were going to divide out with the factors in my numerator. So let me take a picture of these two versions of our function here, and then we'll open up a new page to actually find all this information. Okay, so here are the two versions of our function f of x. So let me just label this. Okay, so this is f of x is equal to. All right, so let's do asymptotes first. By the way, just so you know, x minus 3 squared is also x squared minus 6x plus 9. All right. So, vertical asymptote. I have a vertical asymptote wherever the denominator is equal to 0, and it doesn't divide out with a factor in the numerator, because those are wholes, and nothing divides out, so these are going to be a vertical asymptote, and I have one at x minus 3 equals 0, x equals 3. Okay, so it is important for me to note that this particular asymptote had a multiplicity of 2, and I'll show you why that's important later on when we graph these things. But I knew that it had a multiplicity of 2 because it was squared there. Okay, horizontal asymptote. This is where we look at the degree of the numerator and the degree of the denominator. The degree of my numerator is 2, and the degree of my denominator is 2. So because m is equal to n, I have a horizontal asymptote at y equals the leading coefficient of my numerator, -4, divided by the leading coefficient of my denominator, which is 1. So I have a horizontal asymptote at -4, or y equals -4. All right. Then I have y-intercept, and I have a y-intercept at f of 0. So in this case, I'm going to use my factored form because it's a little, oh, no. Let's see. I'll use my original form of my equation. So my original form was 1 over x minus 3 squared minus 4. It'll just be easier to calculate using that. Okay, so f of 0 is 1 over 0 minus 3 squared minus 4. So that's 1 over -3 squared is 9 minus 4. That's over an understood 1. I need to get a common denominator. 9 over 9. So 1/9 minus 36/9 leaves me with -35/9. So I have a y-intercept at -35/9, which if you do that division, let me do the division in my calculator. 35 divided by 9. Okay, so this is a y-intercept at approximately -3.89. So almost -4. And then finally my x-intercept. That is when f of x is equal to 0. And remember, I only have to worry about my numerator. So when my numerator is equal to 0, 2x minus 7, 2x minus 5, going to use that version. So -1 does not equal 0. I don't have to worry about it, but I could have 2x minus 7 equaling 0 and 2x minus 5 equaling 0. So add 7, and that's 2x equals 7, divide by 2, so x equals 7 halves, which is 3.5. Or I add 5, 2x equals 5, divide by 2, x equals 5 halves. That is the same thing as 2.5. Okay, so I have x-intercepts at 2.5 and at 3.5. These both have a multiplicity of 1. And so this is going to tell us how that thing crosses the x-axis. We've already learned that. Those completely cross since they have a multiplicity of 1. Okay, so here are the steps that you move through to graph a rational function. You find the y-intercepts. You find the x-intercepts after you factor the numerator and the denominator. You need to note the multiplicities of the x-intercepts. Then you find your vertical asymptotes or holes by setting the denominator equal to 0. You also want to note the multiplicity of those because we need to either we need to decide if it has the tendency at that asymptote to act like the rational function or the rational square function. And that'll become more clear when we look at it here. Compare the degrees of the numerator and the denominator to determine the horizontal or slant asymptotes in the sketch graph. Okay, so let's take a look. Okay, so, and notice I restated those steps. up at the top for you. So we're sketching the graph of x plus 2 times x minus 3 divided by x plus 1 squared times x minus 2. So the first thing we'll figure out is the y-intercept. Let me get my black pen. Okay, so the y-intercept is when x is equal to 0. So f of 0 equal to 0 plus 2 times 0 minus 3 divided by 0 plus 1 squared times 0 minus 2. Okay, so this is 2 times negative 3 divided by 1 times negative 2, negative 6 divided by negative 2. So I have a y-intercept of positive 3. All right. So from here, I can go ahead and go onto my graph, and I know that this thing is going to cross the y-axis at positive 3. All right, let's move to x-intercepts. That is when f of x is equal to 0. So 0 equals, remember, I only have to worry about my numerator when I'm talking about x-intercepts. X plus 2 times x minus 3. So x plus 2 equals 0. That means x equals negative 2. And x minus 3 equals 0. That means x is equal to 3. And we also want to note the multiplicity of these. So I have an x-intercept at negative 2 and an x-intercept of 3. And this has a multiplicity of 1, which means it completely crosses. Same thing here. Multiplicity of 1, so it completely crosses there. All right, so I have an x-intercept at negative 2 and at positive 3. Okay, vertical asymptotes. And notice in my original form of my function, none of those factors divide out. So when I set my denominator equal to 0, those are actually going to be asymptotes. They're not going to be wholes. So x plus 1 squared times x minus 2. Okay, so this is when x plus 1 equals 0. So x is negative 1. X minus 2 equals 0, so x is 2. And I'm also going to note the multiplicity, and I'll show you why in a moment. So this has a multiplicity of 2. So I have a vertical asymptote at negative 1. And the multiplicity of that asymptote is 2. So the reason I have to point this multiplicity out is because around this asymptote, this is going to act like 1 over x squared, which also has a multiplicity of 2. In other words, I'm going to have both tail ends surrounding that asymptote be moving in the same direction, either both into positive infinity or both into negative infinity, just like 1 over x squared does. So I'll arrow back here and show you 1 over x squared real quick. Goodness, I was on slide 20 something, so it's going to take a moment. It's all the way back. Okay, here we go. This one on the right, this is, oops, too far. So that's 1 over x squared there on the right. Notice my vertical asymptotes at x equals 0, and both of my tail ends are moving off to positive infinity. Okay, take a look at the vertical asymptote on the left for 1 over x. That's an odd multiplicity. So notice my tail ends are going in opposite directions right at that asymptote. So approaching from the left, I'm going down to negative infinity. Approaching from the right, I'm going up to positive infinity. So that's why you have to note the multiplicity of your asymptotes. Okay, so this particular vertical asymptote has a multiplicity of 1, which means it's going to act like 1 over x, opposite directions approaching that asymptote. So that is an asymptote at positive 2. Okay, horizontal asymptote. Okay, so the leading term of my numerator is going to be an x squared if I multiply all that out. The leading term of my denominator is going to be an x cubed if I multiplied all that out. So my n, the degree of my numerator, is less than the degree of my denominator. Since n is less than m, I believe if I'm not mistaken, if I remember correctly, this means we're going to have a horizontal asymptote at y equals 0. But let me just go back and double check my notes here. Let's go back. So see, even I have to go back and read it because I just, I don't use this all the time unless I'm teaching, especially rational functions. I would like to tell you that you're going to use it in everyday life, but Okay, case 1. Yep. The degree of the numerator less than the degree of the degree of the numerator less than the degree of the denominator. You're going to have a horizontal asymptote at y equals 0. So that was the case with the problem we're working on. And this is why it's so important for you to take notes on these lectures and keep them with you while you're working through the homework so that you can refer to charts and things and steps like that I give you. Okay, so we're going to have a horizontal asymptote at y equals 0. Notice we also have x-intercepts there, so obviously we're going to cross over that horizontal asymptote a couple times, which is legal. We figured out that that's legal. Okay, so we want to note the end behavior according to the multiplicity of the asymptotes. So I have a multiplicity of 2 at that asymptote that is x equals negative 1. In other words, I'm going to have both of my tail ends either going up or down, but because I need to go completely through the x-intercept of negative 2, this part of my graph is going, let's actually start with the y-intercept. So I know I go through 1. Now, this is where you would want to go to your graphing calculator to see what the shape of that looks like. You could start plugging in other values if you wanted to, but we're just sketching. And so what I find out is that this portion of the graph comes down along that asymptote, and then it dips down through and then I go back up. Okay. So, since the multiplicity of my vertical asymptote at -1 is 2, that means that I know that this portion of my graph has also got to go up to positive infinity, because those have to mirror each other on either side of that asymptote, just like 1 over x squared. What I also know is that because of the multiplicity of my other asymptote is 1, it's going to act like 1 over x. That means this side, on this side of the asymptote, I'm going to have to be going into negative infinity. And I completely cross through both of those x-intercepts because they both have a multiplicity of 1 with those x-intercepts. And then what these do is they kind of hook back around and start approaching that asymptote. Same thing here. This kind of hooks back up and starts approaching that asymptote. So that's the graph. Another one. Okay, so we start out with the y-intercept. So f of 0 equal to 0 plus 2 squared, 0 minus 2, 2 times 0 minus 1 squared times 0 minus 3. Okay, so 2 squared is 4, so I'm multiplying 4 times -2, which gives me a -8. And then I have 2 times 1 times -3. That gives me a -6. So this is positive 4/3, which is 1 1/3 for my y-intercept. So I'll go ahead and mark that. This is 1 1/3, about right here. Just above 1. All right, my x-intercepts. And I have those at 0 equals my numerator, x plus 2 squared times x minus 2. So here we have x is -2, and here we have x is 2. Okay, so these are my x-intercepts. This one has a multiplicity of 2, which means it touches and turns there. And this has a multiplicity of 1, which means it completely crosses there. Okay, vertical asymptotes. None of my factors between my numerator and my denominator divide out. So I have vertical asymptotes at 0 equals 2 times x minus 1 squared times x minus 3. 2 does not equal 0. X minus 1 could equal 0. X minus 3 could equal 0. Here x is 1. Here x is 3. So I have 2 vertical asymptotes. This one had a multiplicity of 2, which means it's going to act like 1 over x squared there. This one had a multiplicity of 1, which means it's going to act like 1 over x at that asymptote. Now I guess I should go back and mark my x-intercepts. I have an x-intercept at -2 and an x-intercept at +2. And then I have vertical asymptotes at 1 and 3. Okay, And finally, horizontal or slant asymptote. The leading term of my numerator is going to be an x cubed. The leading term of my denominator is also going to be an x cubed. So, because n equals m, I have that's going to be a 2x cubed down there for my leading term. Because n equals m, I have a horizontal asymptote at y equals the leading coefficient of my numerator divided by the leading coefficient of my denominator. Y equals 1/2. So I have a horizontal asymptote coming through here between 0 and 1 in y. Okay. All right. All I have left to do is graph it. So, I know that looking at my graph on my calculator, I know that I touch and turn at -2. And my x-intercept of -2, I touch and turn. But I have this horizontal asymptote that I'm following along, and I'm sorry this is hard to see, but it kind of dips down and touches and turns. And then it comes back up, goes through the y-intercept, and then follows along that that vertical asymptote. So there's the first piece. Now, that vertical asymptote at x equals 1 has a multiplicity of 2. So I know that this has got to make the chimney here. It needs to come down and cross through that x-axis, and it actually goes down following that other asymptote into -infinity. And then the last piece, I have that asymptote acting like 1/x, so it's the opposite direction, so it comes from positive infinity, and then it comes down to follow that other horizontal asymptote. And you can use your graphing calculator to check yourself with this. We are almost there, I promise. Okay, so this piece of information just tells you you can use your x-intercepts, which are gotten from the factors in your numerator, and you can use your vertical asymptotes and discontinuities to write in factor form your denominator, and that your rational function is going to be in this form of f of x equals some stretch factor a, which you can use any point on the graph to find out once you have the rest of the function written, being multiplied by that polynomial that's created by the factors gotten from your x-intercepts divided by the polynomial that's created by the factors gotten from your discontinuous wholes and vertical asymptotes. Okay, so that's what we're going to do. We're going to try to write a graph for this function that we see here. I'm sorry, write a function for the graph that we see here. So first I'll note that I have x-intercepts at, it looks like, -2 and 3. Well, we know we got those from doing the zero product property. So if I add 2 back to both sides, I get x plus 2 equals 0. And if I subtract 3, I get x minus 3 equals 0. This means my numerator had to have the factors x plus 2 and x plus 3 in them. And so far, I know that the equation of this function in its numerator has x plus 2 times x plus 3. That's what I know so far. Now I use my asymptotes to get the denominator. So I'll just point out I've got an asymptote at -1 and I have an asymptote at 2. So I had vertical asymptotes at x equals -1 and x equals +2. That came from x plus 1 equals 0 and x minus 2 equals 0. So now I know that the factors in my denominator were x plus 1 times x minus 2. Now let's go back and look at the multiplicity of each of these. So if we go back to our x-intercepts, I completely cross here and I completely cross there. That means I have, at its lowest form, a multiplicity of 1 for both of those. Now let's look at the asymptotes. Notice I have different directions on my tail ends approaching my asymptote at -1. That means it's going to act like 1 over x, which is raised to the first power, so my multiplicity is 1 there. However, on the other side, I have this tail end approaching the asymptote into -infinity, and that tail end approaching the asymptote also in -infinity. So that particular factor had to have been squared. So it has a multiplicity of 2. The only thing we have not determined is the stretch factor, some value a, that multiplies by that entire fraction. And so to do that, we choose one point that we know exists on the function, plug it in, and solve for that value. And I'm going to use the y-intercept 0, -2. Okay, so I have, let me get my purple again, -2 equals some stretch factor a multiplied by my rational function with 0 plugged in for x. So I have +2, I'm just making a shell here to go back and plug 0 into. And my x value at that point is 0, so 0, 0. That's why I use the y-intercept, because it plugs in 0, which is nice. Okay, so just simplifying this, -2 equals some stretch factor a multiplied by the fraction 2 times 3 over 1 times -2 squared is 4. So that's -2 equals a times 6 over 4. Yeah. Yeah, 6 over 4. So -2 equals 3/2. What did I get negative? Oh, I'm sorry. That was supposed to be, shoot. Hang on. I have a mistake here. This is a factor of x minus 3. Right here. X minus 3. This is -3. I knew I was supposed to get a negative value, so that makes that -6 over 4. So -3/2. Sorry about that. A. Okay, and so to get that negative 3/2 a off of there, I multiply by the reciprocal on both sides, negative 2/3. Both sides, negative 2/3. Okay, so those divide out, and I have A is equal to, so my stretch factor is equal to negative times a negative is a positive, and 2/3 times 2 is 4/3. So my A is equal to 4/3. So the final form of my function, 4/3, and this is x plus 2, x minus 3, x plus 1, x minus 2 squared. Whew. We have one more to write, and then this lecture's done, I promise. All right, this one's actually easier because they give us all the information we need. Okay, so I have vertical asymptotes at x equals -4 and x equals -5. So that came from x plus 4 equals 0, x plus 5 equals 0. So far, I know that my denominator, I have some stretch factor A, my denominator is x plus 4 times x plus 5. And then x-intercepts at 4, 0, so x equals 4, x equals -6, that's x minus 4 equals 0, x plus 6 equals 0. And a horizontal asymptote at 7. So you have to be a little clever here. That came from y equals 7 over 1, meaning I divided my numerator coefficient, my leading coefficient in my numerator by the leading coefficient in my denominator, which means that the degree of my numerator had to equal the degree of my denominator. So that's my stretch factor. That had to have come from there. So I know that my function, 7 over x times x minus 4 times x plus 6 over x plus 4 times x plus 5. That's it. That's all I got for you. Hope this is helpful.